Hello everyone, my name is Yuris Saputra from University of Technology, Sydney, Australia. Today I would like to present my Globecom paper, namely Selective Federated Learning for On-Road Services in Internet of Vehicles. The Internet of Vehicles has emerged as one of the most promising solutions to enable efficient services for intelligent transportation system, for example, like driving safety and also high economic efficiency. So in this case, based on the Allied Market Research Outlook, the global market value of the IoV will increase significantly by 215% in 2024 due to the high demand of safe driving from smart vehicles. For example, it can be autonomous cars, driverless cars, and electric vehicles. Generally, the road service provider or RSP can deploy on-road service application to improve the driving safety for the smart vehicles in the IoV in a centralized manner. So in this case, first, the RSP can collect the data from active SVs, for example, road conditions, location, and driving activities from the sensing devices, and then the road service provider can also extract the useful information based on the centralized learning process, for example, using cloud server-based learning process, aiming at improving on-road information accuracy. In practice, this kind of a mechanism has been widely implemented by the Google Maps and also the Waze.com to provide high accurate road condition in the real-time manner. However, sharing the raw data, the sensing data to the cloud server in a centralized manner may reveal the privacy of the sensitive information from the smart vehicles, and also it can create a huge network congestion in the IoV network. So actually this kind of issues has been addressed by conventional federated learning, in which each smart vehicle can train the sensing data locally, and then they can only send the train model to the cloud server for the aggregation, global model aggregation. So in this case, the smart vehicle do not need to share the raw data information to the cloud server. However, this conventional federated learning has also some limitations when it is implemented in the IoV networks, because in the conventional federated learning we need to use all of the workers, all of the smart vehicles to share the train model simultaneously. So in this case, it will require excessive communication, especially with the presence of huge number of smart vehicles in practice. And then some smart vehicles also may have unreliable communication channels and dynamic connections. For example, some SPs may be disconnected from the network due to the multiple handovers, or maybe internet unavailability as well. And then some SP also have diverse quality of information. So in this case, the smart vehicles that have a very low quality of information, so it will degrade the whole federated learning process. In this case, we need to provide another effective mechanism. In this case, our proposed solution is location and information significance-based selective federated learning for IoV networks. So in this case, we can select the high-quality workers or smart vehicles to participate in the federated learning process. There are several existing works regarding participant selection in federated learning. For example, C in 2019 provides asynchronous federated learning. In this case, one worker or one vehicle can train or send the local data to the cloud server in an asynchronous manner. And then there exists heterogeneity-based random selection as well by Lee in 2020. And then Young in 2020 also provides random scheduling and round-robin scheduling for participant selection in federated learning. And finally, C in 2020 also provides a local model processing time-based selection. However, these existing works do not consider the location significance and also the quality of information-based selection. So this will be the key factors for IoV networks. So our main contributions in this paper is to propose novel selective federated learning for IoV networks. So in this case, we design the dynamic SV selection to select the best quality FL learners at each learning round to improve the overall learning process with faster convergence. So in this case, we account for location significance and also quality of information based SV selection in the FL process. So in this case, we also provide the extensive simulation using the real world data set and provide the convergence with accuracy 85%. Using only 10% of the active SV in the network. We also can improve the convergence speed by 62% using non-IID scenario and 63% using IID scenario. Yeah, in this system model, we can observe that at each learning round, there are 4 steps to complete the FL process. So first, we need to observe a k number of active SV in the network in the considered area, and then we can choose I SV from this k active SV based on the significant areas. So the significant areas will be classified using the k-means algorithm. And then for the steps 3, we can further choose JSV, which is the subset from ISV here, based on the J largest quality of information value. So in this case, we can choose high quality of information SV, and then finally we can execute the FL process to update the train and also the global model at each learning round. So we first discussed about the location significance based selection. So in this case, we need to select active XV in the significant area. So what is significant area? So the significant areas can be classified based on the average annual daily flow, or AADF here. So this is means the average number of vehicles passing by on major roads on one day in a specific area. So based on this information, we can specify that if we have a higher AADF value, so it implies that the area with higher significance, because we have more vehicles, more volume that may have meaningful information to provide road condition. So in this case, we can classify the significance and also the insignificant areas using the k-mean algorithm. So the k-mean algorithm here is usually used to effectively used to provide classification for binary model here. So this is the optimization problem to find or to classify the significance and also insignificant areas. So we can see here that actually we have 2 binary variables to specify if the total AADF of area A is closer to the centroid of significant or also insignificant area. And then based on the value of 1, the RSP can decide the fixed optimal sets of significant and also insignificant areas to choose especially the active SV in the significant areas for the FL process. After we choose the I number of vehicles from location significant based selection, so we can now move on to the quality of information based selection. So in this case, each smart vehicle I can compute the spatio-temporal variability, which means that this is the data size of collected on-road information in location H for time span G. So we can use sigma here. So in this case, the RSP also need to determine its required spatio-temporal variability at time span G and also location H from SVI. So based on these 2 information, actually we can calculate actual spatio-temporal variability of the smart vehicle I. So it means that it will be equal to the sigma if the actual spatio-temporal variability is still less than the required spatio-temporal variability. Otherwise, we must use the required spatio-temporal variability of the RSP to provide a balanced distribution of the spatio-temporal variability matrices. So now we have 2 matrices for actual and required spatio-temporal variability. So we can use these 2 matrices to calculate the quality of information metric as the normalized spatial length of a metric in Frobenius norm. So in this case, we can see that the value of eta as the quality of information metric is between 0 and 1. So the higher the value of eta, it means that the higher the quality of the information for the selected smart vehicles. After the RSP obtains all of the quality of information metric from ISV, so the RSP can further select JSV to implement the federated learning algorithm according to the largest eta values for each learning round here. So we can find the J number of SV with the largest eta values, the largest of quality of information, and then only this J number of SV can share the local models to update the global on-road information at each learning round. So in this case, we may have different set of JSV at each learning round. For the FL process, we use the deep neural networks with TAN activation function for the hidden layers and also the softmax activation function for the output layer, because we use the classification model here. So for the local loss function, we use the equation to provide the Frobenius norm between the actual label, ground truth label, and also the predicted label. And then for the optimizer, we can use the adaptive learning rate ADAM, which is popular for the deep neural networks. To update the global model at each learning round, so we use the total samples at SV or smart vehicle J, and then we multiply with the local model at smart vehicle J, and then we sum all of this information, and then we divide it by using the total sample, so we can find the global model here. And then we can also update the global loss at each learning round t here by using the local loss function, local loss value at smart vehicle j, and then we sum it, and then we divide it with the total learning SV that we use at each learning round. For the performance evaluation, we use the real dataset from traffic accident, more than 1 million dataset from all major roads in the UK, and then we extract 7 important features from total 34 features, including the location, date, time, accident, intentional condition, for example, light, weather, and also road surface conditions. So we consider this as the training features, and then the accident severity as the training label. We also used more than 200,000 traffic AADFs from 190 areas in the UK to find the set of significant areas. This map illustrates the significant and also insignificant blue set areas. So whether the red area can be considered as City of London, Manchester, Liverpool, Edinburgh, and also Glasgow, while the insignificant blue area will be the other area with less vehicle volume traffic. So we compare our performance proposed solution with the round-robin scheduling RR, and then random scheduling RS, and also location significant only O here. So we can see here that for non-IID scenarios, so the performance of the global accuracy will get better when we use more number of SV at each learning round. At the first figure in the left side, we can see that the performance of all methods will suffer from the very fluctuate global model accuracy, because we only use one smart vehicle, and we know that this is non-IID. It means that each vehicle has very biased data samples. Nonetheless, when we increase the number of SVs, so we can see that our proposed solution, the Pro one, the red one, can improve the convergence accuracy. In this case, we can get the faster convergence for the red one instead of using the round robin and also the random scheduling here. The reason is that the selection of high quality of information SV is guaranteed when we apply the proposed solution. Meanwhile, for the random scheduling and also round robin scheduling cannot even reach the convergence, since they're likely to select low quality of information SV with very biased local dataset. So we get the best performance of the proposed solution when we use the 10 number of SV in this case. For IID scenario, we can see from the left figure, the first figure, when the accuracy using one SV is used, the proposed solution, the red one, still has the fastest convergence compared to the random scheduling, round robin, and also location significance only scheduling here. The interesting point can be observed when we use 5 smart vehicles and also 10 smart vehicles for IID scenarios. While other baseline methods, for example, random scheduling, round robin, and location significant only scheduling, can improve the convergence rate, this trend does not apply for the proposed solution in the red color. This is because with IID local high quality of information dataset at each learning SV, so the aggregation of all local models at the RSP will produce the same model accuracy compared with the case when one high quality of information SV is used. So in this way, the additional datasets with the same high quality of information from other SV will not further improve the convergence speed. Finally, we can conclude this presentation as follows. So first, we develop a novel selective federated learning for IoV networks. So we account for location significant based selection. So in this case, we need to classify the significant area using K-means algorithm, and then we further use quality of information based SV selection using the spatio-temporal variability, and we also derive the quality of information metric to find the best high quality SVs, and then we also provide the dynamic SV selection for each learning round. So in this case, we may have different set of selected SV. So the main goal of this presentation is we want to improve the global on-road model accuracy, especially for the road safety. And then we also demonstrate the performance efficiency using the global model on-road accuracy for scenarios using non-IID and also IID dataset. So thank you for your attention, and that's all of my presentation. Thank you very much.